of. Otherwise, this is incredible magic. It seems out of world. What will come out is somehow crazy, unreal. It looks like a magician trick in which a pigeon turns into a handkerchief or vice versa. But maybe then we should have sort of gotten used to this. So now you tell me which theory should I look at. Now at this point you should be able to identify the model that could be good for me. Sorry? Yeah, what was this? You studied it, yeah? I need more of we spent weeks on this. Which one had S2? SO3, obviously. You need a vector. Vector lives on a... I want you to appreciate that, because otherwise you'll just see some magic happening and you'll never really understand what happened. So it's good to now say, yes, maybe this is not so crazy to imagine that there could be yet another solution, okay?
But do we choose M0 to be S2? And do we have
no, I mean to choose that. I need M0 to be S2 in order to have well-defined map.
Non-trivial binding.
In order to have a non-trivial topology,
It's
right?
the only choice.
Yeah. You won't take, yes. Take a circle and put it on S2 and you can shrink it. If you realize that the rest may not be so incredibly, it's a beautiful thing. It's becoming now one of the most, I would say, fascinating results of physics ever, not just particle physics to me. But I wanted to anticipate. This tells me that I must take SO3. SO3 means that when I say SO3, not SO2, that means really a vector of SO3. In other words, SO3 gauge theory. Then the usual potential, right? D of I. I can write this vector, but my notation may change. We wrote it as a column sometimes it's a vector. Okay, we are familiar with that now. I could remind you, but maybe you help me, you remind me what happened here. What was the physics of this Lagrangian? Remind me what we got here. Sorry?
Goldstone bosons or big particle spectrum?
Goldstone boson?
No,
It's a gauge symmetry. It's a manifestly gauge symmetry, and there will be no Goldstone boson.
Massive gauge.
How many? What happened in this case? Right? It breaks obviously to U1 because I can always choose the vacuum in one direction. That I can't break. I cannot break all the direction. The vector can always be in the z direction. So that symmetry remains. So SO3 gets broken to SO2 if you wish, which is U1. I got a photon. So in the vacuum of the theory was phi, for example, in this direction, and the A3 gauge boson is photon massless. I can still rotate around that direction, MA0. Because of SO2 symmetry, MA1 was equal to MA2. was equal to GV. Remember?
Is this just notation? This always an internal group. Like
Sure.
internal group.
Well, Z, what I mean, third direction.
Okay, but out there.
Let me make you happier. Vector may be confusing. I need a vector, you will see why. Notice what this classical object has, that you are mixing the internal and the space-time coordinates. Okay, this is how you get the object. The string was, remember, the phase was actually theta itself. That was crucial. That made all the difference. Of course, in the vacuum it's not happening, right? Because that cost energy doing something like that it couldn't happen everywhere. So anyway, this was our vacuum. The photon was massless, right? So this is the analog of now your intuition can start working. This is a real photon here. Okay, it was hard to get fermions, okay, but who cares at the moment? Okay, in this theory, this will be a really massless gauge boson. These two guys have to have the same mass. And therefore associate with this photon F mu nu would be d mu a mu 3 minus d mu a mu 3, you agree? This has to be the F mu nu of the photon. It's not F mu nu 3. F mu nu 3 would have an extra piece, but this is. If I thought of, I call it F mu nu because I will call this mu. Let's call it d mu minus d mu a mu. I'm sorry, because otherwise it's confusing. Okay, just to understand. Once it's a photon, it has to have.
When you put a vector arrow on F, it means like the change of F. Right?
Yeah, this is an SO2, SO3. Yes, of course. Now, when I say that I'm looking for a solution like this, I can choose, obviously, phi infinity is this. Okay, now I have options. So, first option, phi infinity is V 0, 0 in the third direction. But I don't want that. There is nothing here. Well, the vacuum is a bit strange, we broke the symmetry, but there is nothing. Energy 0, look how I've chosen it, okay. It's just vacuum. So I will take phi infinity, and now it's better to use a vector notation. But I don't have to, I can write it like this. I can write V, maybe I write like this. This is another possibility. Sine theta cosine phi, sine theta sine phi, cosine theta. Where these are actually spherical coordinates. This is phi at infinity, I'm sorry. So maybe the best thing is that it goes to. In this case, I can take phi equal phi infinity, phi 0, everywhere. That's actually the state of lowest energy. That's good for me to take it everywhere. Costs me no energy. If I take this at infinity, this cannot be true everywhere. Another way of people writing it, people write also that phi at infinity is V times unit vector R. You agree? Or you write phi infinity A component Vxa over R. Okay, they are all equivalent, you agree? This is the meaning, this is the meaning, this is the same thing, right? And this notation may be even the most useful in a sense because we are dealing with a vector. So see what you are doing. You are doing something highly non-trivial, which has this singularity, of course, at the origin. At the origin, you cannot have this orientation. This wouldn't be single valued. So that immediately implies that phi at 0 is 0. There will be a classical solution.
What do we mean by phi equals v times x a over r?
What do I mean by this? This is what I mean by that. That's what, I'm sorry.
Like, I can't imagine how phi looks in that notation. Is it the same thing as the above equation?
That's the definition of a unit vector, isn't it?
What was x a?
Coordinates. X, 1, 2, 3.
Ah, okay.
How will
X.
array? You want me to call them array? No, we call them XA normally. Normally space we call X, the time we call T. So let me stick to the conventional. I think that's what should. Think. You know that the monopole solution, let me call it now monopole as a function of R. I'm going to work in R theta, obviously, spherical coordinates. I'm looking for spherically symmetric solution. Needless to say, is some function V, H of R, no, the best is to write H of R goes to 1 when R goes to infinity, H of R goes to 0 when R goes to 0. And I won't give you H of R, it's irrelevant, we don't care what H of R is. Actually we can do that, people found numerical solutions to this, and in some limit you can even find the analytic form, but we don't really need it. What we want to establish that we will get the magnetic field of a magnetic monopole, and that is so exciting by itself that the rest we can say are just details. But notice complete analogy with the string before. Only now the symmetry is spherical. The beauty of this is now, this is really have the finite energy, not just finite energy per unit length or per unit area. This is truly a compact little ball. So there is a ball of, in other words, it looks like this, here, inside this object. What will be the size of the object? Well, you know that, right? It's 1 over v, okay, that's by now. Inside, we are in phi equals 0, which is the maximum of energy, maximum of potential energy. So that means that because of that, this wants to shrink, right? This wants to go to 0. So that means that outside there is a lot of energy outside that wants this to grow. And that energy, let's help ourselves in order to have an intuition. Maybe I write one more formula from this Lagrangian, that the energy of my static object, I'm always looking for a static finite energy, is R d3r, let me write, there'll be di phi plus v of phi plus 1/2 EA squared plus BA squared. There are 3 electric and magnetic fields. And the energy of a static solution, right, is this plus this plus this. What I need, that this goes to 0 at infinity, you agree? finite energy. And that, of course, means that that's how I get my map. This is what I immediately said. I should leave in my vacuum manifold. Once again, you see it, okay. By asking that di phi goes to 0, you see, if phi is trivial, like in the vacuum, then also A is trivial, the gauge field, and everything is trivial. But notice here that A cannot be trivial, do you agree? So tell me how A will go. What is di phi? Let's write di phi is di plus g ta aa I acting on phi, right? As a column. Or di phi a is di phi a plus g, this let me call it dB, dB, what is T? So there is, no, there is minus Ig, covariant derivative, right? But Tb has plus Ig, so we get plus epsilon B epsilon B A C A I B phi C. Agree? Something like this. This will be 0. Anyway, why am I want to show you this, I'm going to give you detail. Notice that AI, you can tell me immediately how AI will go, you can guess. Yes. Keep this was very useful. We'll come to the technical points. I see immediately that A will go as 1 over G epsilon I A B XB over R squared. It goes as 1 over R. It cannot not go like that because this goes as I said. No, then it's not 1 over R. This is 1. If I write R. This is 1 over R. Sorry, this is 1 over R. This is 1.
We do this because we want to make this vanish.
Oh, this must vanish, right? Oh, I just said, I'm just looking what happens at infinity. Remember, it's enough to know what happens at infinity, you can conclude what the physics is. I had no idea, I didn't have to find the solution at all for the string. I found out that there was a magnetic flux inside. Incredible thing, confined in this flux tube. Okay, I will learn of the physics of the, I will see what this object is just by looking very far from there. This is of course because there are Gauss laws and things like that, and this is great for us. This is why you and I, for example, we can talk about black holes. We can talk about black holes in spite of a fear of getting close to the black hole. So you can say that a black hole has a certain charge. For example, why? Because you can stay far and conclude its properties, okay? That's the beauty of this kind of physics. So you can do the calculation, but imagine what else it will be. It has to be epsilon, there is epsilon there, so it will be epsilon. Even the indices tell you, okay? It could have been delta IA and nothing, but you won't get that. That will be a constant. You get this simply because you will pick up a derivative, okay? So it's going to be 1 over R. Okay, this is a unit vector, and when you take a derivative, you'll get 1 over R. So how will B, can you guess then BAI look like? it's going to be, if I do the derivative, we'll do better than that, okay? You see, there is a suspicion that there could be something that I call the magnetic monopole. Of course, this doesn't make sense, this field. I don't know what this field is. It's some Mills magnetic fields. I don't want to talk about that even. I'm just anticipating that this, just by looking at infinity, I expect that there is something that may look like a magnetic field. With the 1 over r square law. Of course, it doesn't make sense now to talk about these guys. I have to identify the photon field, right? There was my A mu, the field in the vacuum. It has to correspond to the, I need to know whether it really carries magnetic field of the unbroken U1. So this is just sort of the outline of what we have to do. For example, in the vacuum, here is where we need a bigger blackboard. In the vacuum, what is the charge, electromagnetic charge? Sorry?
It's not zero.
It's what? It's...
No, no, sorry.
Trace of T3.
How can be a trace of it? Trace is zero. How can be a trace of... The generators are traceless. There will be a number. No, charge is a generator. Charge is a generator of U1 symmetry, okay? Well, here there is no U1. U1 is hidden in SO3. This is a compact situation. Charge is quantized. Q is?
One time. So this Q is the only generator we are left with after breaking.
Yeah, the unbroken generator. T3. By definition, I took the vacuum in the third direction. Sorry? T3. There was 3 generators to start with. T1, T2, T3, which had their commutation relations. Then I broke the symmetry down to... What does it mean when I wrote this? That U1 remained unbroken. That U1 corresponds to a generator of the group. Which one? The third. That's what you and I do. We diagonalize the third one. I don't know why. We got used to it, okay, from the days of Pauli or whoever did it first. That's how it all started. In the standard model, Q is T3 plus Y over 2. We needed to add the bloody Y over 2 because it didn't give us good charges. You can't do, I mean, I'm worried. I'm sorry. So now that was the failures of Schwinger. Schwinger had an idea. He told studied with Schwinger. He said, why don't I unify? Weak and electromagnetic. So T1 and T2 would correspond to the weak charges. A1 and A2 would form W plus W minus. Some linear combinations we said. And photon would be A3. That's the only choice, and it didn't work. Why? Because of this. Charge is quantized. And charge is not quantized like this. And the end, it is quantized in some crazy manner, okay, but not surely not like this. Not half and minus half, or 1, 0, minus 1. This doesn't correspond to charges in nature. But Q electromagnetic would be T3. What is Q electromagnetic? That's the charge that annihilates the vacuum. And T3 without epsilon had this form. And that of course annihilates phi 0 which is 0, 0, V. Right? This is how we did it. Okay. Now, what about here? What will be the analog? If I choose phi infinity like this, the charge is not T3 that corresponds to this. What is the charge?
The rotated version.
It's a rotated version. Thank you. It's a rotated version. It's a rotated version. Precisely. You can see that Qm is actually Ta XA over R. Let's check it. You see? Go to the vacuum and you will get T3 X3. Or better, let me be precise. Phi A. This is best to write. In the vacuum, phi infinity is equal everywhere to phi, then it's V in the third direction, so I get T3. Okay? So once again, in the vacuum, Q infinity electromagnetic for the vacuum would be TA, and this would be V delta A3, so this is T3. Right? Because I would choose phi A to be V delta A3, that's the same thing as that. Now, Qm, okay, let's check whether this works. This first, this is good, so I'm probably okay, but let's check. I have to get Q infinity acting on phi A infinity. No, I don't want this divided by V. It should be normalized. Phi A carries a dimension, so I should. It was stupid what I said. I wouldn't get T3, it has to be divided by V, right? So this would disappear. I'm sorry, I forgot to normalize. So Q electromagnetic acting on phi A, it actually should be like this to be, what is this? It's Q electromagnetic at infinity AB acting on phi B at infinity. What is the element AB? It's TC. Now you write this. This is XA over R to appreciate. So this is TC XC over R, element AB acting on XB over R. There is an epsilon symbol. Minus I epsilon C AB, something like this. XC XB over R is 0. It's good, it's sort of obvious. There is an anti-symmetric thing here, and then it will act symmetrically. Before I have it white. This is a good definition of charge. Maybe it was, I went quickly, I was summarizing SO3, maybe I should have done it more slowly. You may say this was 2 months ago. Time flies. See how the things can get lost in the noise. You see the danger of the noise.
The subscript means that it's an infinity, or it applies everywhere?
No.
So we should call that
At infinity only. No, you cannot. This is only true at infinity. This must vanish at 0. No, this is a tricky thing. What I write in infinity, this is happening only at infinity.
Okay.
So I want to summarize it. Yes.
When we do spontaneous metropolitan, we always assume the first trivial case where we have vacuum everywhere. And for that case, we always have the same Q electromagnetic, which is T3. But now we only have vacuum at the boundary, not inside, because we have a particle-like thing. So when we talk about SSB, it happens only at the boundary here, right?
Right.
But
Only at the boundary, I mean the vacuum.
okay. Like, well, it's not a problem.
Inside the symmetry is not even broken. Phi is away from the phi is actually zero. Charge vanishes inside.
So only at the boundary we can talk about a photon.
Yeah, you can think about the photon. There is. You can even. So let me write. Let me try to summarize. You see, it's sort of small black words, so it's messy. So let's say vacuum. Phi 0. Or phi 0 A is V delta A3, A mu is A mu 3, and charge is T3. In this, let me start to call it monopole. Phi is, I have to call it phi infinity, is this thing. By the way, do you see that this is a map? This maps the space into group space. I have just mapped the infinity into the group space, into the vacuum manifold. This lives on a vacuum manifold, this one side. I move around the sphere at infinity once, I will cover my internal manifold once. Can you guess how would I do it n times? You're right. Just put n here. That's n, immediate sign. This will do it n times. It's sort of obvious, right? Theta is going slowly. Theta, you go twice around it, you will cover the sphere twice. So you go theta 0 to pi, phi 0 to 2 pi, you're going to cover internal manifolds, okay? So you can always put an integer, okay? We are looking at n equal 1 situation. Let's come later to this. Phi infinity I can write as there, so let me not write it again. Maybe better, phi infinity A is V xa over R. Charge at infinity is Ta xa over R. Which is that what I wrote there. And the photon would be this sort of projects the thing. Now how would you show that? You have to compute the mass matrix, so I give you a little exercise. Let me not do it now. It's in my notes. I could do it in 2 minutes. You put this, when we put the value of 0, we got the third component. When you see it, you will see that guy's masses. What will be the, can you guess what will be the electromagnetic field? This will work, this will correspond. Let me write it. I can write it just to be clear. I can write it F mu A phi infinity A over V to be sure. Now, the thing is, you may say, I don't like the thing that you should object here, but I don't know even if I should say it, but maybe it's correct. You would say if you use this formula, you know, that means you are generalizing this to F mu A for any Fa over V. Then you say, well, what will you get when you go to the vacuum? You should ask me here, you should. I'm sort of doing your job here, but I could have just gone on to see how much it will buy you. Is this really a good definition of F mu nu? It sounds, look at the charge, look at this, it sounds right. But if it is good, then when I go to vacuum, it should reduce to the one in the vacuum. But notice what this would reduce when this is in the third direction. What will I get? In the vacuum, I will get F mu nu 3. But F mu nu 3 is d mu a mu 3 minus d mu a mu 3 plus g a mu 1 a mu 2 minus, probably with a factor of, there is epsilon, right? Probably a factor of 2 here, I don't know, doesn't matter. Or maybe even, let me just write it, minus a mu 2, maybe not a factor of 2, this is a different thing, a mu 1, the famous epsilon piece. So it's not reducing. This is not. It seems that I'm wrong, because it should be this. Because the photon was a mu 3, and I cannot have this extra piece in electromagnetism, okay? And sort of it takes some thought to figure it out, and Hoff did. Hoff is not completely stupid. I didn't read Podyakov's paper, by the way. They did it independently in 1974. This incredible Bob Shell comes up with. So he says it should look like this. He says, what is the definition F mu nu 1? In the vacuum, it must reduce to this. And it should not depend on the direction of the group space. F mu nu somehow should, you see, not arbitrarily depend on the definition of the group space. It should be the ones you fix the definition, okay? So it should be a group invariant in the group space. So when you live in a particular, why am I saying this? Because you could have chosen this not in the third direction, in the first direction, so I should get a good result. In the second direction, or in all three directions, okay, or whatever. So it should be a group invariant. Because there is a symmetry in the problem that is only broken spontaneously when you fix in which vacuum you want to live. So the expression, however, has to be group invariant, and in the vacuum it should reduce to whatever you had. So here is the expression of it Hoff. I mean, on the other hand, it should be like this. You know, there are two things. This should obviously correspond to this. So how do I reconcile the two? It turns out that actually it does reconcile, because after a little thought you find out that F mu nu has to have this form, F mu nu A, phi A over V, or you could write phi A of the, you can even just think of the, just write like this, absolute value of it. Minus, and now is it 1 over G, that's why it would be good to have minus epsilon ABC di phi A, no, d mu phi A, d mu phi B, phi C over phi Q. Something like this. There may be a, I don't remember, it's something like this. What I mean, it's relevant because this goes to 0 at infinity. For us, it turns out that this actually is a good thing, but it will reduce. Here you have to fix the coefficient so that when you go down to the vacuum, it cancels this piece. And that's going to be precisely here cancelled. You will see when you go to the vacuum. Please check it. I can pause here, just to.
So the definition we got at infinity for the charge and the photon field, they are fine. But then to define the F mu nu,
You want to have F mu nu, which doesn't depend on the. You are saying, forget even this affinity, forget the monopole. You are saying, I have a theory that breaks down to U1. What is the form of F mu nu that does not depend on your particular, moment of sort of. Funny desire to be in whatever direction. I can choose, you remember, the physics cannot depend on which directions you live. Who says that you have to rotate the vector in the z direction? In the sun model, you can keep the vector in any which direction. He says you will check here that F mu nu is good. Why? It's a group invariant, it reduces to the thing that you have in the, and it has a unique form. This coefficient is fixed here. I think it's correct what I wrote, but it may not be. This will be fixed in order that you get rid, because in the vacuum you know how the photon looks like. This helps you. For us, this is irrelevant. For the monopole, this goes to 0. Therefore, this is good. As intuitively you would expect. Because this is the projection here. It's not the third. I'm now spherically symmetric. Okay? This is just a unit vector. Instead of being in the third direction, I'm in a unit vector on a sphere. It's a unit vector in the sphere. So I'm taking F mu nu and taking a unit vector. I expected this to be a good F mu nu, and it's fortunately it's good F mu nu. It will reduce to the. This is actually good F mu nu, but for the monopole, it works. So all I have to do now is to sit down and compute this F mu nu.
Actually, when we write down Q&A to match with the electromagnetic, step to go F mu nu was kind of naive because we thought it should be proportional to A mu, and we write it in the same method. But if you try to really calculate it, we need to take the covariant derivatives and commutators of them. Like, can I get this result just by computing, or does it take more thought to write this result to show that this is the real F mu nu?
How would you, without thought, how would you have? I'm not sure.
I have the definition of F mu nu as the commutator of two covariant derivatives, which includes the A mu that we wrote there, and from there I get.
So how do we get this? If it's just by checking which term we should write.
I did it by checking. Good question. You put me here. I'm not sure. Maybe.
So it's enough to say I want to write down some group invariant term that eliminates the A1, A2.
Right. You can with a little thought you can guess, because what you have to eliminate U1 and U2, and because take it in the third direction, you will see that 3 will give you here 1 and 2. You will play a little bit. It's an easy exercise. And he had to have this form in the field, so in order to give me two gauge fields. It had to be a group invariant. I can't write a group field, I can only write the covariant derivative. I need vectors there. It's a vector, but it's maybe similar to what you're saying.
And the next step piece comes from that commutator, and if I plug in that A mu, maybe it will give. This should be like complicated.
Find D mu, it may be complicated, I don't know. It would be good to have an equivalent way. Think about it. I haven't. I mean, to me this was convincing. I never even thought very much about it. I remember being surprised because I didn't read the Koch paper, I don't know what I was reading, then I was reproducing the things. I was very happy, and that to me looks like a good F mu nu. Then later on I realized that, okay, well, it's a little... if you are doing a spherically symmetric thing, and if you're projecting everything on the unit vector on a sphere, the charge, the photon, and everything, then obviously, as you know, it's got to work. But it's good to know that it also agrees with something that can give you vacuum. This form is unique that Hoff claims that that sounds convincing. How it has to be a group invariant, it has to have the what other vectors you have. You see, these are the vectors d mu and d nu. This is just a normalization. We can pause here because this calculation is long. I don't want to do it. This calculation is quite long. We have to remember how okay, let's still pause for a second. Well, why you are thinking, because from di phi going to 0, I have to find ai, and then I have to find phi ija, and then static, of course, there will be only ij, there will not be electric field that we see, all the time derivatives are 0, and then I have to, from here, compute fij. And it's straightforward, and actually it's not hard, it's just long. Because it's only a first derivative to take in both cases. I mean, the first piece here, that it's epsilon, this comes out immediately, x a over r squared, x j over r squared, 1 over g. There is this interesting 1 over g, that you had to be there. And it's nice, it's not a perturbative result. You see, we're getting something which is 1 over g. We are not expanding in g as a singularity in g equal to 0. Obviously, we are not around the vacuum doing our perturbation theory. Okay? So, while you are thinking, I can just tell you that when you do the calculation, you define bi, which is 1/2 epsilon I jk f jk. That's called the magnetic field. And you follow the calculation, and I would strongly suggest you to do it. You sit in here. Don't wait for some other moment. These are greatest moments to learn some of the most exciting physics that I can imagine. Bi gets to be 1 over g xi over r cubed. You get G in magnetic monopole to be equal 4 pi over G. Yes.
I'm suspecting that the way we chose our vacuum is at the boundary, is winded around the S2, determines our charge somehow. For example, if I didn't have a cosine term that winds once around the whole sphere, maybe I couldn't get any monopole there, right?
Well, you had no options. You either wind or you don't wind. The maps are very trivial. It's not for you. Either n is equal 1 or n is equal 0 and n is equal 2. You now choose. You live in the vacuum manifold. When you live in the vacuum manifold, you have to tell me what it is. Absolutely true what you said. But that's either that form that I wrote or phi equal vacuum.
Okay, so then if I start rotating,
you want a single value field. You want a field that is well defined in the. It was like the circle. You didn't want to write some theta over 2 or something. You understand? It was n theta. It was good to do the string. That's why I changed my mind and did the string before. Just there you see.
So if I don't change anything around,
then you have a vacuum. There is nothing in between. There is nothing in between. There is a vacuum and then there is this beast. If I have put n or Emilio's n, what would I get?
n times.
You will get here n.
Yes.
And we will get here n. Notice that this reminds you of. I mean, what have we done? Dirac says, if there is a monopole, charge will be quantized. Tchov-Polyakov say, I take the theories where charge is quantized. The charge is always a linear combination of the original charges, and that's traceless, therefore it's quantized. The eigenvalues are fixed. Okay? T3 is a nice example. Therefore, I suspect that there is a monopole, even without looking for any solution. Okay? Then comes all this analysis topology. Okay? We are now sort of finding a deep connection between quantization of charge and nature is the existence of monopoles. I will bet any money in the world that monopoles exist. I can't believe that they are not there. Okay? I don't know what that means, unless you're willing to bet. Then I can define it, okay, in terms of quantity of money that you would bet.
But there is no convincing argument that charge is quantized. In standard model, there is no, right?
Well, the anomaly wanted charge to be quantized. But that didn't mean much to me. There was no prediction or anything. It didn't tell me that all the particle charges are quantized. In a theory like SO3, all charges are quantized. There cannot be a particle which is not, whose charge is not quantized. Doesn't matter which representation you take. When you have a single compact group, non-abelian group, where the generator are the traceless, the charges will be related. The tracelessness will always tell you that the charge of a quark and lepton is related. Now, I don't know if you remember that first we got a very interesting monopole. Notice that the charge of the monopole is 1 over G. But that's what the Dirac told us. At the end, we have to agree with him. Dirac says that the product of magnetic and electric charge is 2 pi times n. And in this theory, remember GZ. In this theory, GZ, assuming that this is the correct theory. I'm pretending that the standard model is based on SO3, that this is the real photon. I'm speaking of a real photon with a real electromagnetic field, or better to say magnetic field, so that we have a real magnetic monopole. Okay. Now notice that Dirac says, who is general, he doesn't care how you get a monopole. He says G monopole times E or Q electromagnetic charge, let's say Q is better, is 2 pi n. It's interesting that we got a factor of 2 difference. Can you guess why? It sort of tells you that the smallest charge times Gn will be 2 pi n, says Dirac. Okay, not 4 pi n. Actually, they are in agreement, these formulas. Between when I have SO3, I took a vector representation. There is also possible to introduce a spinner that has a charge half. So it's true that G is 4 by 2, but if I put now an electron in the theory, I don't know how to call this object, okay? It's not an electron with a charge. Then I will get 2 pi. They perfectly agree. The smallest charge in SO3 theory is not 1, it's a half. That becomes SO2, of course. That's what we wanted to do. That's how I studied my course. There are a few more things to say, but we still have some time.
So now all the discussion we did for the strings on the wall, there will be some spherical object with a lot of energy inside. We can compute the energy, the size.
We will come the same way. We can actually put the can do that, but I mean, I'm just trying to think what we can do. We'll again say that the size is 1 over V. That would be easy to do. You see now you can even anticipate. Inside there is a Higgs field, so that wants the guy to shrink. But the smaller it is, the more there is magnetic field outside. Okay. Once you leave the magnetic monopole, there is a magnetic field outside. We should maybe write that. Sorry, is it?
Yes, that's the one.
Let me. We had this. This is electromagnetic tensor. And then from here we find that Fij something like this. A straightforward this was a vacuum. This is our monopole. So it looks like this. Inside is Higgs field, and outside is magnetic field. By the way, when I write this form, this is at infinity. This is true only far from the monopole, right? When I'm far from this object at infinity. It's not like Dirac monopole that it has some structure, so around the structure it's messy and complicated. But since just to get a feeling for the size of the monopole, in order to get a monopole I need a non-abelian group to break. So I gave you an example of SO3 broken down to U1. You can also find out that if you do this symmetry breaking, you also get a monopole. Of course, it's not that simple, but there is a beautiful paper by Tomaras and Dokos that actually show and construct these monopoles. That it's easy to see, here it's not so easy to see. Then you take my word for it, okay? Basically, almost always when you break a compact group down to U1, you will get monopoles, okay? I don't think that they are, they look a bit funny, they don't have this very... The scale of this theory would be what we call n GAD, 10 to the 16 GeV. It could not be less than that, because proton would decay too fast, that we've seen. And actually unification, when you look coupling constants, when you run them, it all fits. Therefore, the size of the monopole V, which is 10 to the 16 GeV, in other words, the size of the monopole, how should we call it? R monopole, is 10 to the minus 16, 10 to the minus 13 centimeters. Surely, macroscopically speaking, this is like Dirac monopole, right? Who cares?
This resulting group breaking SU5 can be Sandra model 1 or it's different.
Sorry,
The SU3 cross SU2 U1. This one can be the Sandra model group or
yes, this is the sun model group.
because
Precisely.
you can add in the lift
Right.
and it doesn't change anything in the fact that you have SU5. If you have SU2 just with the lift component, For SU5, you still have left and right asymmetric or it will be.
Well, SU5 is said a few words, okay? This will be an interesting, another course in some other, you will hear about it. SU5 works like this. You have a neutrino and electron, and you will have 3 quarks here, obviously. So you have DC, DC, left hand. This is SU5.
Okay, so it's SU5
Color?
left, that one.
Sorry?
So the one that we write there is SU5 left, not the
No.
the 4. Okay.
Well, no. No, you can't say that in SU5. You see, this guy is left-handed, but this down quark is right-handed. And it feels SU5. The electroweak part is working here. So, this guy doesn't have, why do we call SU2L? Because this guy doesn't have weak interaction. This is a right-handed quark, remember? Because this is an anti-quark. Left-handed, right? DCL is CDR bar transpose. Particle anti-particle change chirality. Yet in SU5 this guy has an interaction. There are new gauge bosons called X. Actually, there are 2 types of gauge bosons, you can see them immediately, you don't have to do any calculation. There is one guy that will take this into an electron, call it X. There's another guy that will take it into a neutrino, call it Y. SU5 has both left and right particles.
The right components of electron and neutrino are singlets under this SU5?
Sorry?
The right component, neutrino and electron, is a singlet under SU5? Or no?
No.
They go in
They're
there.
that giant.
No, how could it be a singlet under
That's
SU5? Then there will be no SU5.
they don't. Okay, they should fit.
They are not singlet. Electron is not singlet under the standard model.
So the right components goes.
Electron carries charge. Electron is not a singlet. It's a singlet under SU2, of course, but it's not a singlet in a generic sense.
Because it has.
If you are a singlet to SU5, you carry no interactions, okay? So the standard model is inside SU5. So if you feel the standard model, you feel SU5 for sure.
So if we restrict ourselves for the SU2 subgroup of SU5, then right-handed components are the singlets of the subgroup SU2.
Sure, well, you reproduce the standard model, of course.
Okay. So we're
That you have to make sure that you get the standard model right. And the way it looks, the representation SU5, there is a left-handed representation, which is 5-dimensional, and then there is a left-handed representation, which is, or right-handed in my notation. Let's think. No, it's correct. It's anti-symmetric. It's 10-dimensional anti-symmetric. So here is the strong interaction. Here you put UC. There are 3 of them. This is color, so there is U, 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 D, 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 left-handed. You see now I got, this was DC left-handed, now I got D left-handed. I get U left-handed, but I get UC left-handed. UC doesn't feel weak interaction, he has only strong interaction. This guy has, of course, both. Weak interactions work here in the SU2 space, the strong interaction works here, and here there is a positron. A positron left-handed is a right-handed electron, okay? This is how, I mean, that.
Does it feel big first?
Does it?
I can't see.
Front block, the weak block. Is it the one?
Of course.
The 10, well, it's,
the one that has both.
it's,
That's what it is.
10 is 5 times 5 bar anti-symmetric. So for example, you see here came from 3 times 3 bar anti-symmetric. 5 times 5, sorry, how can you do 5 times 5? 3 times 3 anti-symmetric. Okay, you can symmetrize and anti-symmetrize only the same representation. 5 bar, you just make traceless. Okay, that's a joint. 3 times 3 anti-symmetrics is in SU3, that's 3 star. That's this guy. For example, this guy you got, you see, 10 is 5 times 5 bar, but 5 is just to 3 1 plus 1 2. Color SU2. So when you take 5 times variable combination 3 times 3, 5 times 5, which will be 3 star, that's UC. Then there will be combination 3 times 2. Here it is. 3 times 2. Then there is a combination 2 times 2. Anti-symmetric. So how will it look? It will look 1C 2L times 1C 2L anti-symmetric. That's a singlet. 2 times 2 is a singlet, so you should know it, obviously. This is anti-symmetric. How can you see free interaction? Does it have a partner? So you knew that there is only minus it because it's anti-symmetric, okay? But that's a famous way of getting a singlet when you anti-symmetrize spin. What I show in my notes, let me just write it here. Then ask me questions about SU5 if you wish, or whatever.
So this, the vacuum manifold also should be as to indicate for the map we want.
Sorry?
So we want the vacuum manifold to be as the same as the infinity manifold to have this non-trivial map.
Yeah, sure, you need this.
So
Well, it's actually, you have to generalize this. It's not that simple. You have to generalize. You won't see easily this vacuum manifold or SU5 breaking down to SU3, SU2 cross U1, that you won't visualize. But infinity is the same infinity, so obviously it has to be S2.
so the beginning.
That you won't see that. There are people find this topological variant, let's say homotopic class pi 2 called whatever. That has to, I don't want to give you a simple, it's hard to see SU5, vacuum manifold SU5, broken to SU6, SU2, SU1.
But it's not trivial as all three. Okay, of course.
No, it has to be, in some sense. There must be a map. So in other words, it must be mappable. It must belong to the same homotopy class, what they say. Well, I don't want to. Let me try not to enter that. Yes, it's. You have to show still that you have the same integer and so on. Okay, the same map of like S2 map and S2. I just wanted to say that you can show that there is a conserved current proportional to this is a unit vector of phi. You can see that this current is conserved. You can see that the charge K0, this current is conserved trivially. It's again the topological current. I didn't write it for the string, I don't remember. But this you can see just because of the symmetry and anti-symmetry of the derivatives, okay. And K0 you will have to show is the magnetic charge. I do it, you know, you integrate over K0 and you show that it's an integer. I do the calculation properly normalized, of course. It's integer in some units. You can put something here, okay. The thing is to show is that delta times B is K0. It's proportional to K0. Let me write like this.
Now this B is
A B is this field Fij, right?
of the photon.
You actually show that, I don't know, that d mu f mu nu tilde is equal to k nu. This is what you show. By the analogy, this you can show, you just normalize it. It's a bit lengthy calculation, but it can be done. I don't think I showed this in my notes. I showed that when you integrate this, you get an integer, something I show, something I don't, but this can be shown, and this is precisely the dual of the electric field, right? This is a magnetic field.
To show that it's an integer, the K0 comes from also
For that map I gave, you put that map for the map that I gave with that 10 that Emilio said. You remember? You write phi of the monopole, let's call it a monopole at infinity, is sine theta cosine n phi. This is my unit vector. This corresponds to this.
And now the FMU will be more complicated than the one we wrote for SO3. But at infinity.
Oh, how does this magnetic monopole look like?
At infinity.
Oh, you can, well, you are in the eternal space of a group. No, it's more complicated. You have to find the electromagnetic charge and so on. Really, what we are saying here, let me think how to say this here. I think you and I would say that F mu nu, that a good F mu nu here, probably what we would say, that this F mu nu is proportional to the trace F mu nu, or let me write with F mu nu A, okay, I can just write like this, trace F mu nu A, TA times Q electromagnetic. I think this is F nu, what I wrote here. Because Q, for example, Q electromagnetic, there is this extra piece that has to be subtracted of it. I'm looking at the first piece. That piece vanishes anyway in the, but it has to be included. Notice that I think this is correct because Q electromagnetic was T3 in the vacuum, and this will give me delta A3, it will give me F minus 3, and there it was TB XB over R, which will project this thing. Okay, so if you go to SU5, now you have to isolate it, Q electromagnetic and so on. So there are this monopole, monopoles who carry color and so on and be confined. You can have all kinds of things now in SU5 because it's now mixed with it's a very, very interesting paper that classifies the SU5 monopoles.
And the experimental search, so these monopoles should be.
Unfortunately, monopoles have not been seen. Maybe we should just say we have never been found. People who support the astroparticle limit from the magnetic field of galaxy and so on by seeing indirect effects. But there was an experiment, macro experiment at Gran Sasso that looked for them for many years, and they didn't find them. They put the limit of flux of the monopoles is less than about, I think, 10 to the minus 15 per centimeter square per second. Whatever that means. I don't know. That's less than what you get when you look for them. The thing, but now it's getting late, that is interesting. The question is, if you believe that the universe was hot as we do, you could ask yourself how many monopoles should have been produced in the early universe in the usual picture of symmetry restoration. You would say that the universe, remember how we started with the domain wall? We said that when the symmetry is restored and now I am cooling the universe down, I will get plus minus random thing. So they say you will get a domain wall where the Higgs field is oriented like this. Then there'll be a domain wall when the Higgs field is oriented like this. Then there'll be a domain where no domain wall, a domain. So the idea is called the Himmel Mechanism. He says, I expect to have sort of a monopole per horizon. Because it won't, roughly, more than the horizon, the field will not orient itself in the same direction. I may get half of the monopole horizon or 0.1 and so on, but roughly in order of magnitude. Does that seem reasonable? Monopole has this sort of hedgehog called Polyakov called it, orientation magnetic field like this. It's not that crazy, okay, roughly in order of magnitude. Some people say that you could get more, but people want to say you won't get much less than 1 or 1 in 10 or 1 in 15 or something, okay? They won't continue over horizon to organize themselves. We can try to estimate what will be the energy density. I don't know, I'm getting tired. Let me try. Getting weak somehow. Let me think. So if you have one monopole per horizon, one monopole. And the temperature is 10 to the 16 GeV. That's the relevant temperature. That's the scale of the theory, right? The monopoles, the first monopole we find in the grand unified theory. So what would that mean? How many horizons did I have? R over dH Remember I gave you the formula, it was roughly 10 to the 30. Do you remember that there is a formula like this? Well, remember, because R is roughly 10 to the 30 over time, and dH is roughly m Planck over t squared. Remember this, the horizon, the time, temperature, gravity has to enter there, okay? Don't write 1 over t, please. Okay? It can be here, this is just the assumption of the adiabatic expansion that nothing is lost. Okay, this is... So at 10 to the 16 GeV, what do I get? Tell me. What is in Planck? You don't know what in Planck is? No, it cannot be. You had a course on gravity. No, how? No, it cannot be. You cannot not know what a Planck is. How? Huh? Roughly? No, it's not that big. It's 10 to the 19 GeV. So I will get 10 to the 27. So I get 10 to the 27 horizons, that means, but actually to get the number of monopoles I should take this cubed. Not 10 to the 27 horizon, I'm sorry, this is the distance. We have to speak of the volume. So the number of horizons really would be, or number of monopoles, would be how many? 10 to the cube of this. Well, I exaggerate, this was 28 really, I cheated, so let's put 25. 10 to the 75, there are a lot of monopoles. So how much energy density we would have in the monopole? 75, how many, what is the energy of the monopole? Mass of the monopole is 10 to the 16 GeV. So we would have the energy in the form of the monopole would be 10 to the 75 to 10 to the 16. It's a bit naive because you may say, could Eric have annihilate? I don't know, this is a little naive. So maybe I should just stop. 10 to the 91, around 10 to the 90 GeV. How many baryons there are in the universe? I should have taken 10 to the 30 here, just to give you a feeling. There are 10 to the 10 less baryons than the photon. How many photons in the universe? The number of photons n is the density of the photons times the temperature Q times the volume. So this is RT cube. This is a number, it's actually a cube of this huge number, which is 10 to the 84. No, yeah. So they're about 10 to the 74. This is the number of photons. So how many baryons in the universe? 10 to the 74. So there are 16 orders of magnitude more in the form of the monopole. This is called the monopole problem. And people took it very seriously. You have to study it a little more carefully, but roughly the problem really is like that. And that of course destroys the Big Bang picture of the universe. It's too much, okay? You understood what I want you to remember this number. There is this very strange number. The universe 10 to the 28 centimeters, but also R times temperature is around 10 to the 28. the funny thing between GeV and the
The fact that we don't see monopoles means that should be
to Alan Wood here, actually Henry Tai and Alan Wood started to worry about that. He came to the inflation worrying more about the monopoles than about the horizon problem. Then people thought about that. Now inflation says that there were not many. The idea of inflation was you start with one horizon and you exponentially grow. So according to inflation, people like this. You solved, I find this sort of mind-boggling that you can like that. You are saying that you started with one patch, so there is one monopole in the universe. That's the monopole that went through Cabrera's place on the February 14 of 1982, okay? So I find this a terrible solution to the monopole problem, and I hope that it's wrong. The most beautiful prediction of any physics or beyond the standard model, particularly grand unification, existence of magnetic monopole, I don't see anything much more earth-shattering. You can go and tell anybody, go tonight, have a dinner, and tell the cashier that maybe there are magnetic monopoles. People will appreciate this as an exciting thing. Okay, this would be a great thing. I've spent a lot of time, spent years, thinking about alternatives, hoping to find a picture in which you would actually not have too many monopoles, but have monopoles, okay? An alternative picture.
So inflation only works on the fact that there's a single horizon that exponentially grows in this world.
Right.
But there are like different schemes where it's not a single horizon. But
Well, we don't know when inflation took place. Inflation could be taking place. That all depends. If inflation took place earlier than that logic, you should be careful because you may start producing monopoles anywhere. And anyway, it's not established.
neither monopoles cannot decay neither. So
No monopoles cannot decay.
so there is no reason that we don't see them if there are some according to this.
Well,
Which are the
in order to produce them, you need this phase transition of symmetry restoration. That is the only way. That was the picture I drew. That there was a domain here and a domain there. That will happen only if the high temperature symmetries are restored. There are actually counterexamples to that. And I mentioned this when we came up with this, that to me most original work I ever done in my life was not, unfortunately not original. Well, I've done some original work. Okay, I don't know if I should say that. I didn't. Original in the sense of implications. We found out by playing Mohapatra and myself that there are examples when symmetries do not get restored. And of course, people told us, distinguished physicists, that we were idiots because this is simply a entropy argument. You want to go to the more ordered or less ordered world when you go to higher temperatures. So for sure there must be symmetry restoration, people argue. The question is not whether there is symmetry restoration, but when. Sure, eventually the symmetry may be restored. Imagine that the symmetry is restored above Planck scale. Then you don't have to worry about this because this happens. You don't know what happens at the Planck scale. It turned out that it was interesting. Some of these people that criticized us were colleagues of Weinberg at Harvard, but they didn't read this classic beautiful paper of Weinberg of high temperature. He actually has noticed that didn't make any physical use. Oh, we did, but we spent a year, we couldn't publish it, okay? Turns out, Weinberg actually found a system in nature, it's called Rochelle salt. He read about it. As encyclopedic as he tends to be, immediately found the example. We should have done the same. And salt, when you heat the salts, they melt. Salts are crystals. They melt as you would expect because melting is being less ordered. Actually, Rochelle salt, when you heat it, gets more ordered, gets more crystallized. For a huge range of temperature, finally it melts. So it seems that the argument, physical argument, that eventually you will melt or that you will be restored, seems to be correct. Everything tells you. But it could happen not at the temperature that you expect naively, which is this scale which happens. In that case, for example, it's not clear what would, because we don't know how gravity works. So this was in 79 we made, but some years later, Dwali and myself, Melfo and myself actually applied this to grand unified theory, showing that you could have maybe another way of dealing with it, in which the numbers is not produced a la Kibble, but they could be produced. I'll make this story short. It's not yet established. What will be the mechanism, if any, to solve the monopole problem? Okay? Inflation is very elegant, beautiful, simple, and even convincing, but it's tragic because it kills the most beautiful. So I don't like it, for sure. To me, existence of magnetic monopole is somehow a dream coming true. I wasn't even aware. I remember once I spent a year at CERN, and Cecilia Jaskog, at that time she was a member of the Nobel Committee, and she stops me in the corridor and says, what do you think would be most important discovery? You know, she wants to see how people think about, they're always gauging people to see how you feel about discoveries. You see, they have to give these Nobel Prizes. So I said, let me think. She says, no, that's what I don't want you to do, okay? Because, so without thinking, I said magnetic monopoles. I wasn't aware at all. That surprised me a lot. Because I didn't know I worked much more on other aspects, even on grand unification, proton decay, neutrino mass, whatever the things that I worked on were not monopoles. But to me, somehow it just happened naturally. And I think when you think about it, no, it's incredible. That's sort of the first thing you learned as a child, that there are no monopoles, and now you find out that it's very convincing that there ought to be there. Charges quantized. I'll stop here.